Okay, so instead of having a ball being whirled in a vertical circle on a string, it's being whirled in a circle somehow on a rigid stick. But nonetheless, the stick acts just like a string in that it's constantly pulling the ball inward. So basically, as the ball goes around, the stick is going to be pulling inward on the ball and basically acts like a tension force. So, number 45, they say, find the tension when the ball is at the 3 o'clock position. Oh, no. They say, when the ball is at the 3 o'clock position, the stick tension is 16 newtons. So, when the ball is right here, the stick is actually pulling in on the ball with a tension force of 16 newtons. Now they also tell you in the problem that the ball has a mass of 0.20 kilograms. And they say that the ball is whirled at a constant speed. So the question is, when the ball is at the 6 o'clock position down here, how much is that stick vertical? If it was a horizontal circle, then if the tension was 16, it'd be equal to 16. But it's not, because it's a vertical circle, and you got gravity pulling down. So basically, we know the tension at the 3 o'clock position, which is right here, like when a clock's at 3 o'clock, is 16, and we want to know, well, how much tension is in that stick at the 6 o'clock. Well, since it's constant speed, no. It's circular motion, though. Okay? And remember, with circular motion, even if something has a constant speed, it has a centripetal acceleration towards the center. What about the direction? Well, I don't know if you remember from our circular motion.
Please, one interruption. Hallie Kaufman, please come to the main office. Hallie Kaufman, please come to the main office. Thank you.
When the object's here, it has the tension force acting in on it, and it has its weight force going down. But when the object's down here, it's got the tension in the stick pulling it up, but its weight force is acting straight down.
In this case, tension force?
Is what? No, T is the tension force.
Is it like a normal force?
It's like a normal force. No, a normal force is like from underneath pushing up. This doesn't have a force underneath pushing up. This has a stick on top pulling up. So it has the same function as the normal force. So, I don't know if you recall, but for that point there, if you apply the centripetal force formula, what force is going to be providing the centripetal force? What's the expression that I'm going to substitute in for F sub c at that 3 o'clock position? only the tension.
What about
The FG in no way, shape, or form is pushing that object towards the center of the circle. There's no component of FG that's acting along the radius. It's perpendicular to the tension force, so there's no component of FG that's playing a role. So basically, we know what that tension force is. They told us that the tension force is 16. So we know 16 newtons equals the mass, which was 0.20 kilograms. Times v squared all over the radius. Oh, did they give us the radius?
No.
Alright, so they didn't give us the radius, huh? So I guess we're going to have to solve in terms of the radius. Not a problem in terms of r. So if we solve that,
Oh wait, we need to solve it in terms of v squared over r and substitute it.
I think we just better solve it in terms of r, for the velocity. Because we only know the velocity. You know what?
Well, what are they actually asking for? Are they asking for
No, you're right. You're absolutely right. We could just solve for the v squared over r. Because if the velocity is going to stay the same, the radius is going to stay the same. You're absolutely right. So basically, what would v squared over r be equal to?
80 newtons over kilograms.
So it's going to be 80 meters per second squared. And basically what that is, that's the centripetal acceleration. Now down at this point over here, if it has the same velocity and the same, I should say same speed and the same radius, then what's going to be the deal with the centripetal acceleration down here at this lower point?
It would be the same.
It's going to be the same.
Wait, so from this point would it be the mass going to times 80 equals f of t minus sub g?
Yes. Yes. So now when we're dealing with that 6 o'clock position, we know the centripetal force equals the mass times the centripetal acceleration. But as Dave said perfectly, the expression for the centripetal force now, T minus Fg. And we know the mass, so we can figure out Fg, that's going to be 0.20 kilograms times 10 meters per second squared equals 0.20 kilograms times 80 meters per second squared. And if you solve that for t, and how should that tension compare down below?
Higher.
It's going to be bigger.
18.
Sometimes the question will ask, at what point in the vertical circle is the string most likely to break? And it's just like asking the question, at what point in the vertical circle is the normal force the greatest? At the bottom.
It was at the top, which the T plus FG.
Yes, exactly.